Okay, great. So, again, I wanted to make a point. I don't know if you are all able to install Jupyter Notebook and Python on your system. Okay. John, your own is already installed. Okay, you were with us in the beginning of the class.
Yes, it's done.
Okay, and I'm seeing Chuku Kalo. Chuku Kalo, are you there? Can you confirm if you're with us?
Yes, I'm with you. Thank you.
Oh, great. Were you able to install the Jupyter Notebook and Python?
I think I already, first of all, I don't have the invites, but I think I have.
Okay. Okay, great. Great. Okay, nice. So, what we were going to do, so if you're not talking, you will just mute so we can be able to all follow from the same angle. Okay, so back to what okay, great. And I think all the materials are said. So I'm going to be sharing my screen, and I'll be asking you if you see my screen. So can you see my screen now? Can you all see my screen?
Yeah, so it's visible.
Yes.
Oh, great. Thank you.
Yes.
Okay, thank you. So, last week we kind of briefly. So let me just make a recap from our last class. So last week we started talking about more of the concepts of supervised learning. Basically, we focused on the regression and classification technique, and last week we highlighted some of the key methods in supervised learning. Basically, we talk about the regression algorithms, we talk about the linear regression, we also talk about the decision tree and the random forest. So I wouldn't want to go over them again. If you really want to know much about them, you just take a look at the class and grab the concept. And then we also talk about the logistic regression, the support vector machine, the random forest, and k-nearest neighbor. Now, we consider this classification algorithm as the simplest, or in other words, we call them the traditional state-of-the-art models. The reason is because these methods are sort of interpretable. When we talk about interpretability in this case, we're looking at the complexity of our model. So when you look at all the model we discussed from our previous classes, there are models that are quite simple, they are quite explainable, though to some certain extent we consider random forest and support vector as black box. But when you're looking at the interpretability ladder, they are still considered as highly interpretable compared to things like deep neural networks. So we'll be coming back to deep neural networks. Later on we'll be talking about these complex models and how you could use them. However, what I always tell people is that whenever you want to build your model, start with the simple ones and then you climb to the complex one. The reason is because there is no one fit size all approach. Meaning you cannot just say this model is good for all problems. No. Each problem you're confronted with, explore the simplest model and then you build to the complex model. And then last week we also talked about hands-on and practical examples in Jupyter Notebook and with Python. Then on the regression example, we talk about the housing problem. And then on the classification example, we talk about the breast cancer problem. So again, if you have not watched the class, you could, watch them. And if you want to rerun the script, I put a link where you could be able to download the script and rerun it in your own PC to see how this model works. And again, like I told you guys from the onset that you cannot do data science in isolation. You can't do AI. You just have to keep running them. make those errors. Don't be afraid to make them. So each time you fail, don't just give up and say, oh, I'm running into errors. Rather, try to understand why that error comes in, and then how do you overcome those errors. So feel free to rerun this script, and when you get into errors, let me know, and anywhere I could help, I'm always willing to help you. So, but know that these are just the basics one. So today we're going to be building on what we have done from last week. So today I'm going to be taking you through a very different thing. We're just going to look at how do we evaluate these models that we have trained. How do we make this model better? So, like I said, a recap from last week, we talked about the regression and also how to build these models and also the practical section. But you need to make this model better. How do you improve these performances? So, in order for you to evaluate your model, in order for you to evaluate your model accurately, you need to understand what is a good model and what is a bad model. Because in the real world, you will not likely find the models that easy. You're always going to be confronted with problems that you will discover that, what you actually had learned in the class is not fitting in the real world. But that doesn't mean that what you learned in the classroom is not right. But it's just that the real world is very difficult for you to be able to estimate. So what you need to do is to understand how your model looks like. What is really the problem? Where is the model? How do you tweak this model to improve this performance on new data set? How do you trust what the model is giving to you? So all these kind of questions will come up. For example, when we talk about the housing problem, you can get into a situation where your model will be predicting that, oh, it makes a lot of sense. But at the end of the day, if the model is not predicting the right thing, you can get bias that will become very angry. Then, on the case of the cancer, especially like in the area of whenever you're building model in areas that are sensitive, like finance, in area like healthcare, you don't just deploy anything out there. And the reason is because what you feel is right can affect the lives of people. For example, in the area of stock market, if you develop a model that actually tells the stockbrokers that they are going to make lots of gain, and then they invest their money or their clients' money, and then it turns out that it actually went down, maybe because they didn't foresee some sort of economic collapse. And then you can't just go back and begin to explain to them, oh, I made a mistake and all that. You're definitely going to run into trouble. The same thing with in area of health. There is this book by Christopher Moore. He talks about interpretable machine learning models. Then he started his book. I love reading a lot about his book. I do follow him on social media posts. He started his book on interpretable machine learning. He opens it up by telling us about a patient that was in the hospital, and then the patient died as a result of overdose of a particular medication that was given to him. So one of the team sat down. The lady, the doctor, one of the ladies in the team sat down, and she was going over and trying to, figure out what went wrong. And she came up with the fact that probably if they could have watched what the algorithm was doing, they wouldn't have followed the instruction of the algorithm and gave that patient those overdose. And they could have probably saved the life of that patient. But they lost the patient because of the carelessness of the machine learning algorithm. So when you are in an area like healthcare, you are making decisions that are likely going to impact lives. So you don't deploy anyhow model. Anything you're deploying, you have to make sure that it is something that at the end of the day, it will save lives and not destroy lives. And now that's why machine learning could be good in the hands of good guys. it could be bad in the hands of bad guys. And if you have time, you could look out for a book called Weapon of Mass Destruction. I was talking with one of my colleagues the other day on a project we are working on currently. We're trying to write the proposal. We're looking at some of the adverse effects of paper mills in the era of generative AI. So we get talking, and I was telling her, I said, there is a book I read some time back during my PhD called Weapon of Mass Destruction. And the reason the lecturer brought it up then to us was to make us understand that this knowledge in the hands of the wrong people can be destructive. So we brought out that talk because we were like, considering the way AI is going, democratizing AI for everyone to dip into, also knew that even the bad guys could get into it. Now, for us, in someone in Nigeria, for example, we have a history of attacks from Boko Haram. Now, imagine Boko Haram having so much knowledge of AI. They could be able to automate so many things. For example, drones. They don't need to go to sensitive places in person. All what they need to do is to sit back and plan how to attack those places. So we must be careful to find a way to checkmate these systems so that they don't just go out there and begin to cause havoc. And we must put some sort of regulation on it so that it doesn't again fall into the hands of the bad guys. So when we talk about open source, you need to also question what this open source means. Do we keep saying these things are open source and everyone, including the bad guys, could access some of these things for destructive purpose? So a little digress. So let's get back to what we are saying. So evaluating your model in terms of regression algorithms, what you're basically going to be looking at is things like the mean absolute error, MAE. And this is just the average prediction error. So what you do, you look out for how is this capturing the variation in your data set. And also another metric is the mean square error. The mean square error sometimes is much more trusted than the mean absolute error because it's kind of capture a wider variation, especially in the test set. So a lot of people focus more on the mean square error. So you'll be seeing many people talk about the RMSE, the MSE in regression problem. Another very important thing is the R square. The R square is usually gives you the percentage of the variance or the variation that was able to be captured by your data set. So through those kind of measures, you will see if your model is doing well or is actually doing very bad. Then in the area of classification problem, basically we'll be looking at things like so sorry, before I talk about these measures, our classification problem in itself has different types. We can have a binary problem and we can have a multi-class problem. So I will be talking about more of those things in our next classes because, like I said, I want us to start from the simple and then we build up to the complex. So basically what some of these metrics that you are seeing here are still going to be the same when we start looking at complex problem. The only problem is that there will be a sort of a shift because now we are focusing on a very larger or wider complex things. So basically some of the performance metrics you will be looking out for is things like the ROC AUC curve. For me, most of the time, I don't trust the accuracy score. And I'll be telling you the reason why very soon. So most of the time when I'm doing machine learning tasks, I quickly check how my ROC curves and scores looks like. Is it really making sense or is not really making sense? Because the ROC AUC tells me the area that are actually confident that this thing was actually making the right decision. So most of the time I looked out for things like that. I remember when I was doing my work during my PhD, I was looking at this bunch of genetic variants that were contributing to severity in COVID-19. So the variant itself are not enough for me to get a lot of signals when I'm making predictions. So when I make prediction, the accuracy will be looking kind of good, like 65, 70%. But then when I looked at the ROC curve, I'll be having things like 55, 40 something. And then I'll be like, no, something is not adding up here. So then I now begin to explore other things, future selection and all that, to get a better performance. So the ROC always gives you a good, and even when you are building systems and you are deploying them in form of apps, you'll be seeing the ROC most of the time. And even in hospitals, they use some of these things to show, for example, when you put patient in ICU, you'll be able to see some of these metrics and know if the patient is doing well or is doing bad. Another very important metrics is the confusion matrix. The confusion matrix helps you to be able to see the ones that are correctly classified and the ones that are misclassified. So back to the accuracy score. It is a very popular score. Almost most of the machine learning tasks you see, lots of people uses the accuracy score. But this accuracy score, one of the problem it has is that once the data is slightly imbalanced, the accuracy does not reflect the true performance of your data set. Then you begin to have things like it begins to favor the dominant class. And most of the time, the dominant class is likely going to be the class that you are not interested or the negative instance. So the positive instance that you are interested in, you discover it is a rare occurrence. So for example, for Zeg and Onoja that are in the area of malware, probably you are interested in defects of those things happening, but you discover the chances of these things happening is very small. So you will likely have a data set that the target variable will be much more of things that are not malware compared to things that are malware. So when you go for things like accuracy score, you're likely going to have a good performance, but when you go back into the hood and begin to investigate things like confusion matrix and ROC curve and F1 score, you begin to now see there are some sort of imbalances coming up. So what you now need to do is to find a way to account for that imbalances. However, the accuracy score is a very good way of also assessing the performance. So you don't discard it, but just have it in mind that it is not a perfect score. So the recall, is also there. The recall is just the sensitivity of your model. How sensitive is this your model in recognizing the actual instance you are interested in? So another one you talk about is the precision. Like we always say, precision is just about being precise. Are you actually picking up the right things in your model? So it is always focused or tilted towards things like true, positive, and false positives. When we go on that, I'll be telling you much more about some of these things. And then the F1 score is just the harmonic mean of the recall and the precision. So most of the time for me, I always like to check the F1 score to see, because it's kind of telling me about the sensitivity and also the specificity of my model. So it means that if I really want to assess the model, I should take note of these things. I should, especially the F1 score and also the confusion matrix and the ROC curves. So they kind of really give you a hint of how your model is performing. And then when you're going to be deploying your model in the field, sometimes you're doing it blindly because based on what you have trained. So it's better when you have a good overview of this model, so you don't just put it out there and then it begins to make a lot of mistakes. I don't know if you followed the news recently. I was following news on X that Elon Musk have to recall, like I think about 30 or something, I think 30,000 of those his electric cars or something, because he discovered they were having issues with the driving wheels or so he have to recall them back. So these are some of the mistakes that you don't want to make them. So you just have to ensure that whatever you are doing, you are not having issues with model, especially when you're deploying them out there. So when we talk about improving our model, what we are going to be looking out for is overfitting and underfitting. Now, like I said, I'm always trying to find words that will keep those things simple. When we talk about overfitting, basically knows that overfitting is always something that you have to struggle with in almost all what you are doing. And what it means is that if the model is too complex for the data if the data set is too complex, most of the time you will likely going to begin to use complex models. So I gave you guys example last week that logistic regression is a very simple model, for example, in classification tasks. So most of the time when you use a logistic regression, we do call it the sort of initial model, or sometimes we call it the baseline model. We call them baseline because these models are very, very simple. But what it does is that it gives you a hint about the performance of the model. So most of the time, if you use a logistic regression, for example, on a complex task, you're likely going to get a very average score or even a worse score. So maybe you get like a 55 or 65. And then maybe it's a task that involved you to use a lot of precision or a lot of accuracy. So you cannot just settle for that 65 or 55 that you had. So what you're going to do is, okay, you want to explore other models. Like I said earlier on, that don't settle for one model. Try different models before you can know that which model fits your problem very well. So by the time you are looking at a complex problem, you try a regression, it did do well. Then you try something like a decision tree. You discover that the performance will slightly or even improve more. Then you also said, oh, I don't want a decision tree. Let me try another model. You try a support vector or a k-nearest neighbor, or you even moved it to random forest. As you continue to increase the bar, you're increasing the complexity. And this is a problem between interpretability and explainability and also black box, because the more you shift the bar, the more you include so many parameters in your model, and the more it becomes difficult for you to explain what is happening in the model. So the overfitting is likely going to be focusing on the training data set. So most of the time in the training data set, you are going to be having biasness. And the reason for this biasness, it could come up from so many angles. It could come from the fact that you have issues with dimensionality of your data set. It could come as a result of some missing values. It could even come as a result of multicollinearities. It could come from as a result of you, the researcher. Because, for example, I'll give you an example of a particular algorithm that was used in the United States before now to classify a kind of disclassify or classify crimes. So they noticed that something was wrong with this algorithm, in a sense that when a black-skinned person commit the same crime with a white-skinned person, and looking back at their history, the black-skinned person do not even have history of those crimes. But looking back at the history of the white-skinned person, he had so many crimes. He broke into houses, he did this, he did that, he did that. But they noticed that the model was scoring the light-skinned person lower than the black-skinned person, even though the chances that the crime is going to occur in the future for the black person is very low compared to the light-skinned person. So they noticed that, so they begin to investigate the problem, that what's wrong? Why do we have this model tilted this way? And then they discovered that it was from the persons that trained the model. So they trained the model to favor or skew it towards a light-skinned person. The same thing happens when we begin to talk about convolutional neural network. You will discover that in cases like cancer, a black-skinned person, it's very difficult for the model to detect. And then it's easy for it to detect for a white-skinned person. So the reason is because the model was trained with more pixels of a white-skinned person compared to that of a black-skinned person. So when it sees that of a black-skinned person, it could easily arrive at a false conclusion, and you will take it and run with it if you don't investigate the problem. So the issues of biasness could come from you as the researcher. So that's why whenever you're doing research, you have to try as much as possible to be transparent in reporting what you have done, because that could help in reproducing it by other researchers, and they could easily spot the problem. Like I told someone, research is not, you're not competing with people. Rather, you are trying to fill in a void that humanity is striving hard to understand. So when you get to understand these things, you will not be greedy or selfish in sharing what you have found out. Because when you share what you have found out, it gives room to a lot of evaluation, and then subjectivity can come in. And people could begin to say, oh, why not you try it like this? Why not you try it this way? Why not you do this? Why not you do this? And I totally understand one of the reasons why, for someone coming from an African background, when you're doing your defense during undergraduate, most of the time, it's like a war room, it's like a war situation. You don't, it's not like some people that wants to learn new things on what you are doing. There is this tense atmosphere. So sometimes you can speak out lots of gibberish, you could lie, you could do all sort of things, because you're put under this tense direct condition that you don't know how to. But in real sense, research is not supposed to be done that way. It's supposed to give you that room for you to say, this is what I have learned from this process. Then somebody can come in tomorrow and say, okay, we have discovered this, what this person have done, and then we can be able to do it this way, and we could get better results. So it's all about contributing to the body of knowledge. So the best model is that model that has to be in between. That in between, in this case, is the sweet spot, or we usually call it the sweet spot, that place at which the bias and the variance had a trade-off. So it's called the bias variance trade-off. That's the point at which you should be always looking at when you're developing your model and when you want to improve your model. The reason is because whenever you moved a bit, you increase the complexity. You're likely going to have more variation in your model. You will begin to see lots of, the model will seem very nice. Oh, I'm having 90%, 100%. But in real sense, you are actually overfitting the problem. Then on the other hand, if you decide to say, okay, let me just settle with a less complex model, you are leaving a lot of knowledge or patterns out that you're not picking up. And in that case, you end up underfitting the problem. So these two things that has to struggle between them, in the religious setting, you said the spirit is willing, the body is weak or something. So there is this, it's like a trade-off between the two worlds. How do you balance this underfitting and overfitting thing? So much so that you don't have to completely, be on one side of it, because you could see that being on one side of it, you're actually not helping yourself. So you could see in the case of the high variance, which is overfitting, you will discover that you are actually fitting the training data perfectly well. So when you see the score, sometimes you even see 100%. But something will begin to happen when you deploy it to the field. You will notice it actually go down. It begins to, capture nothing, because all what you were capturing was nothing but noise. So you did not actually capture patterns in your data set. So you must always recognize that having a very high training score is not the ultimate, but how will it reflect when you deploy it? Do you capture really nice stuff, or it was just some noise, some random noise that you were picking up? So you have to look into these nitty-gritty things whenever you are developing your model, so you can be able to actually make sure you deploy a robust model out there. While when we talk about the biasness, like I say, it's just this shallow way of, it's a simple, just like I said, you use a simple model like a logistic regression to fit the problem, but you left so many things out. You will see in this case of high bias, we're actually not capturing things that are up here. We're only picking things between this point and at this point. But anything up here and down here have been left out. Then what we are looking out for, which we say is the good model, is that one that it's not that it's capturing everything, but it's not leaving everything out. The reason is because it's actually following patterns. Because when you look at this data set, you could clearly see that there is a pattern that the data formed. But how do you get that model that will fit this pattern is what you would always be looking out for. So you are not trying to say you're building a perfect model, but such that the biasness will be very small and also the variance will be very small. But like I told you, in the real world, it's not always going to be like that. You will struggle with those things, and it's just how these things works, because sometimes we have not really perfectly understand how these things are. There are so many things that contribute. For example, when we talk about COVID-19, when I was building my model during my research, I came to realize that genetics itself was not completely what is causing the severity of the disease. There were so many unexplained things, like if the person is a male, if the person was older, if the person had some previous history of multimorbidity. For example, people that were having at risk of cardiovascular diseases, they had high chances of, when they contacted the virus, they reacted, to ended up in ICUs, and some of them even died. And so many people that had issues like chronic kidney disease, they were reacting differently. Then we now discovered there was this set of people that they were young. They did not have any of those history of these diseases. They don't have cardiovascular disease. They don't have kidney problem. They don't smoke. They don't do all the risk factors that medical personnel highlighted. But they were falling sick when they contacted the disease. And I don't know if you've seen recently about the vaccine, where a lot of talk was going on about the vaccine. Some persons once they take the vaccine, their immune system, everything completely collapsed, and it becomes a serious issue. And this person doesn't even have any history of sickness or something, but they reacted negatively to the vaccine. So there are so many complex factors that sometimes your model cannot be able to account for it. But what we are looking out for is if your model is actually giving us a clue. Is it really pointing to a direction that could actually help us in understanding the problem? Like they said, no one knows it all. So at the end of the day, what you're really trying to do is say, this is a little I have found. Then somebody pick it from there and run with it. For example, I was reading some articles some days back about generative AI, and people talk about this, and somebody pointed out an article from 2015 where the article talk about attention is all what you need. And then I was like, oh, let me check this article. And then I went back to read the article, and I discovered that, oh, this person talked about this thing in 2015 in a conference. And that was how people picked it up and started running with it since then. And now today in 2023, from 2023 November, that was when ChatGPT, came up, and everybody started talking about generative AI, and large language models and all that. But these things were there. People were building on them in the process of time. So that's how this knowledge culminates. So that's why we must be careful about what we put out there to make sure that it is something that people can actually take it and run with it. So when we talk about low variance, you will notice that there is a kind of a concentration of the model. So it's going to fit it, but so much so that there is no much deviation. The pattern and everything is being observed, even though there will be some that are left out. But during the high variance, you will see that mostly what the model is capturing is noise. But you could see here that the model couldn't really fit the problem very well. So they kind of really scattered all over, which are mostly just bunch of noise that is capturing. But again, when we talk about high biasness, remember from the model here, you notice that it's only one portion it will capture. It will completely mix out large portion of the data set. So that's not, again, what we want. So we just want that which, could actually tell us a story that really, really makes sense, So in order for us to overcome this whole issues that I've outlined, we need to carry out what we call hyperparameter tuning. We need to make sure we tweak the models such that we could be able to minimize this high variance or high biasness in our problems. So another way we could also be able to understand better is cross-validation. Now, like I said, all what we are trying to do here is we are trying to find a way to make our model not to capture noise, to make our model not to be picking signals that are not true. So that's why we need to keep tweaking, these parameters. And like I said, the model doesn't hold the whole truth. Okay, so sometimes you would tweak and tweak and tweak, and you won't see a difference. That tells you that there is also a large portion that you cannot be able to account for them. Which so it's pointing out to you that maybe you need to collect more data set. Maybe you need to research the problem to understand it better. And I'm going to tell you, this is a real example. I did a project some months back with PedBright Institute. So I was in this meeting, and then we talk about some of the things they were doing. They were looking at antibodies, heavy and light chains, that they wanted to use it for production of vaccine, the mouth foot disease in cows. So they usually test in the lab, but however, they discovered that they had to do a lot of testing in order for them to get the actual heavy chain that will pair with the light chains. So they felt that if machine learning could come in, it could help them to prioritize the heavy chains that are useful, so they don't have to waste a lot of resources going back to the lab each time to run in order to validate these things, because it costs them a lot. So when they told me about it, at first I said, okay, fine, we could be able to do something. Then they sent the data set for me. So when I saw the data set, these were a bunch of peptides, like a combination of amino acids. So at first, I was just looking at them. I was like, okay, I got into work. I did some background check, and I was like, okay, now it's fine. But then I came over. I told them, I said, okay, the problem we are having is we need to show the machine what example of a heavy chain that pairs with a light chain, and the example of a heavy chain that does not pair with a light chain. That way we can train it and then we tell it. So when we ran the first one, we got these good scores. But then I told them, I said, look, I somehow feel this problem is not sufficient because it seems we need more data set to understand these patterns. So luckily for them, they were able to run and get some 5,000 more peptides and send it to me. So when I got those things, I kind of again reran the model. There was this back and forth we we're going, but finally we developed the model and we finally converted it to a web application, and then I send it over to them. And now it's kind of really helping them to prioritize what they want to do in the lab, so they don't have to, keep spending a lot of resources. So what you're doing with machine learning basically is to really help you to get that right thing, so you don't have to keep, reinventing the wheels and, putting a lot of resources about that. So when you have a data set that is not enough, you will find a way to manage the data set, because machine learnings are data hungry. The more data you give it, the better. So for me, I will tell people get more data as much as you can. But there are situations where somebody do not have those data sets. So what do they have to do? They have to find a way to minimize it. So the best way they could go about minimizing is for them to find a way to split the data and repeat the process you continue to iterate, go back. So that way, the model could be able to actually pick in what is true and what is not true. So that's why you use approaches like cross-validation to also split the data into random partitions. And then at the end of the day, you can be able to see if the process is coming up. I don't know if you're with me, and do you have any questions so far? So I don't just keep talking. Are you all with me, and are we all on the same page?
Yes. Yes.
Great. Okay, great. Thank you. So when we talk about model tuning, like I said earlier on, we tweak the parameters. We are interested in how do we continue to, just like imagine somebody that is cooking. When you are cooking, if you overput the salt, for example, nobody will want to eat the food. And then if you don't put salt, people will complain. So the tweaking is just like consider yourself in the kitchen preparing recipes of different things. So you have to put in different things to make the food delicious. But in this case, what you are cooking is the data set. So you're going to be adding, and subtracting, searching, and all that. So the problem is that if you want to do this thing manually, you cannot be able to exhaust the space, and you don't know which of them is the right parameters. So what you need to do is for you to be able to automate the process so that you can be able to do it for you without you having to be involved in doing it manually all the time. So what we do in automating it is using the approach called grid search. So the grid search will help you to search this large space of parameters. For example, if I'm training a random forest, and the random forest most of the time we evaluate it based on the depthness of the trees. So let's say you're looking at 50 estimators, 10 estimators, 20 estimators, 50 estimators, 100 estimators. In fact, you could even make it up to 1,000. But like I said, of course, you shouldn't increase it a lot because you're still going to have risks of overfitting. But the more the space is big, the more the machine will have to search all the space. So it will be taking a lot of time. You will notice that once you increase it, you have to have the computational power because these are hard NP problems. So do make sure when you're taking those parameters, don't start with big parameters. No. So what you will do is that normally it's not even in all cases that you need to perform the grid search, okay? But it really helps you if you optimize it so that you can be able to identify the best model for the problem. So the hyperparameter setting again, it's basically on the training, so prior to the training, that's when we set up the hyperparameter, and then we subsequently begin to test it to see how it performs. Don't worry, I think when we looked at the practical, we can talk more about how these things are done. Then the cross validation, like I said, if you don't have large data set, what will you now do? Do you have to keep going back? Imagine some of these data sets are expensive, and again, there's one of the things I learned when I came to Europe, that data is very important. Data is your privacy, it's your power. Data is the new oil. So when I was telling my wife the other day that when I see in Africa people keep posting data on everything they do, I keep laughing at them because your data is being collectively used to actually determine and predict everything you want to do in the future. So you can't just give up your. And I think one of the sweet things of life is privacy because you keep people wants to know. In fact, if you give people the room, they will enter into your bedroom to know what you're doing. So the privacy is very, very important. You don't just give it up like that. But there's this thing about us in Africa. I think we said we're producing content, but we don't know actually we are feeding the algorithms with a lot of information to be able to determine us. And if you notice, if you've been on Facebook for a long time, you will notice the improvement. The Facebook in 2010 is not really the same Facebook now. Now there are lots of features, lots of things, lots of tags. So you begin to wonder how, but the information they were collecting from the previous times, they were using it to retrain the recommendation model. And now you see that the system looks very, very okay. So, but that's like they created a kind of a sustaining system. But suppose for someone that do not have this kind of platform to keep collecting the data, what will you do? You need to come up with a way that it will help you to manage this data set. So normally in the traditional setting of machine learning, when you get the data, you prepare the data into machine format, meaning you're going to do sort of future engineering, you're going to handle missing values, you're going to remove irrelevant features, and all that and all that. Then when you now have the final data in the format you want it to be, you will have to split it into training set and testing set. And like I said in my previous videos, that training is usually large. In fact, if you can make it 80, 90%, it's fine because the testing set is what you just do once. So it's not really a big deal. But the problem, and again, one of the problem I think some people like to make the testing set a bit large, like 30% sometimes, is the fact that sometimes there are instances that the training have not seen. And the testing will just give them very nice thing. But once they put it in the field, it begins to misbehave. So they wanted to see really what, but the problem they are having is that you're depriving the training from learning more things. Because the more the training learn more things about the data, the better it becomes. So you begin to see reasons why the training set have to have the chunk of the data and not the testing set. So, but again, it depends on rationale and also the importance of what you're doing. But I always say be careful because the testing is not really useful to you. It just validates, it's like an exam. So imagine what is useful to you is the preparation before the exam. Anything after the exam is not important to you. So you have to be very careful about the data you put into the testing. So make sure that to a large extent, let the training be much more larger than the testing. And then what other people also do these days is that they further split the testing into two. So you now have testing, internal testing, and a sort of external testing or evaluation, or validation set. So after they train the model, they test the model and then they validate the model. So what they do is when they keep 20% for testing, they further split it into 50-50. Then they keep the remaining 50. Then after the model is ready, they've tested and everything, then they check it and see what's happening. So, but again, it depends on what you're doing. But some of these approaches are very good, so you don't put in a wrong model in the market. So what the cross-validation does is that, and again, it depends because I've seen cases where when you're using cross-validation, you don't need to split into training testing. Rather, what they will do is that they will take a portion and keep it aside and say, okay, this is for the final testing. Then the whole thing that they have in the training, they split it and then they test. So what the cross-validation does is that when it takes the training, it will partition them randomly. So if you are saying I'm partitioning it into 5-fold, it means in each of these folds, you will have a training and a testing, 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 like that. But usually K is not bigger than 10. So you don't really see people having a larger K like 20, no, just K-fold usually in fact, 5 is okay. For me, I feel 5 is fine because when you look anything beyond 5, you really see it's kind of, there is no much information gain. So you can use 5, but some people use 3. So again, it depends, but usually 10 is the highest. I'm not seeing anyone using more than 10. So each of these fold here, you have a training and a testing, a training and a testing, a training and a testing, a training and a testing. Then they will also use the grid search. So when they use the grid search to find the best parameters, they use the cross validation to test, to train and test on each of the fold. So by the time you do those rigorous approaches, you subject your machine learning model to a more robust way in coming up with decisions. So that's very, very important. So take note of this thing. So like I said, the aim is to make it to generalize well on the testing phase and validation phase. So you don't deploy nonsense in the field. So we're going to be entering the practical section of the work. So I think what I'm going to do, I'm going to send you the script right now, so you could also be able to open it from your end, and then we could be doing it together. I think that way it will be much better. But before we go to the practical section, if you have any question, feel free to ask me. And any question, anybody that wants anything you don't understand, I'm fine. I'll explain it to you. It's fine. Okay, I think the script we're using. Okay, good. Okay. Okay, so I'm going to share the script with the group. Okay. Thank you, Monday. Okay. So I have sent the script to the WhatsApp group. You can be able to download it. It is it is a Python script. So you can be able to sorry, it's a Jupyter Notebook. It's an IPython. So you can be able to run it if you have a Jupyter Notebook and also a Python install. I think that's the prerequisite for them. But if you don't have it, it's fine. You can go back and watch the previous videos, see how you could do the installation, and then you could run the last video or the last script of the class. I think John, you can help us to send the last script in case people that wants to run that, then they could try it and see. Then you could have a proper understanding. So maybe you could share the last script after this class. It's fine. They could try it out. So in order for you to open the Jupyter Notebook, you need to just come to the search button of it. So you will see the command prompt. And if you are using Mac or Linux, you just need to. Okay. Before we go in, I think there is a question. Somebody asked about. Sorry. Okay. I think there is a question from Benjamin. He said you like clarification on cross validation. He said if you said the K should preferably not be above 10, does that mean collectively the training and the testing make up the validation fold? No. So what happened in the cross validation is that the testing said the final testing, you only do that once. You don't make it inside the cross validation. No, you just keep that one separately. But when each of the fold in the training, you are going to split it into a training and a testing. But now, the reason why I said it should not be above 10, the reason is because if you have more than 10, the computation will be much. And then, despite the computation that will be much, you will not really have much improvement. So the improvement you are going to have, rather, you will notice it from the 1 to 5 fold. Anything 6, 7, 8, 9, 10, there won't be much. You see a little improvement, no improvement like that. So it's more like if you occupy space without doing much, and then it's taking your time. I don't know if you understand. So I usually tell people like 5 is fine. You don't need to go beyond that. So that way you can be able to save your time and also the computational space. Imagine if you are using your CPU for training these models. It will take like a whole day. Sometimes it can even shut down your system if you don't have a lot of space. So again, it's kind of I'm not really a fan of this heavy computational stuff, except if I have to use a GPU or cloud computing facilities. So you have to make sure that you don't really keep exhausting your space for nothing, because your RAM will be hot and heated and all that, and these things. I have trained models that took me days and weeks, even on a GPU, so at the end of the day, you can imagine if it's taking me weeks on GPU, that means on the CPU, it will take maybe more than a month, maybe 6 months or something. So again, you just have to prioritize some of these things so that you don't keep yourself, hoping, and then maybe these things run and the improvement is very little. At the end of the day, you wasted your time, your resources, and then it goes. And these things consume a lot of I think that's one of the effects of AI that the world is currently talking about. This generative AI, they consume a lot of energy. And I don't know if you followed the recent wildfire in California and the rest. I saw news that were accusing AI companies that they were the cost of it, because they have to cool off the servers, and then they took a lot of water from the dams and the lakes around. So that way, when the wildfire starts, they don't have water to quench it. They have to be waiting for the fire service to be able to do that and all that. So that's one of the problems right now we're trying to avoid in these models. And that's why DeepSeek was quite a challenge for the Silicon Valley, because they were so surprised that these guys could do the same thing that we did with so much resources at a very minimal cost. So at the end of the day, you have to really be putting these computational resources into check. And especially, for someone on the African continent, for example, you don't really, let me use Nigeria, because I was in Kenya, they did have electricity, so I wouldn't talk for other countries. But for us, somehow in Nigeria, imagine you have to be the one to buy your electricity and solar energy and all that. Now, these things will now come and take all the energy to use it to power the model. It could be challenging for you. So usually make sure you go for approaches that are not computationally expensive as such. And if you must use these computationally expensive things, you don't have to train them on your local systems. Rather, you could use cloud facilities like AWS and all that. And we'll be talking about those things as we moved on. So each of the training, you split into training, each of the folds, you split into training and testing, training and testing, training and testing, training and testing, until the K fold. However, if you have just 5 of them, it's better, because you saved yourself the remaining 5, which will not have to take all your time. So I hope my response is clear. Any other question? Okay, thank you. Okay, so if we don't have any question, let's start the practical part. So
sorry.
the first thing, okay.
So like apart from the computational overhead, does having a more care value validation value fold does it enhance the performance of the model in any way than having a less like 5K validation fold?
No, I think it doesn't, because I have seen a situation where I used 10 and I didn't get any better performance than 5 and even 3. So it made me realize, like, why waste my time, trying to. But my reason at the initial point was that I was feeling, if I have 10, at least I will have a large knowledge of everything. But then I discovered it didn't really improve anything. However, some people do leave 10, but I've never seen above 10. It's usually 1 to 10. No, 2 to 10. Not, we don't have less than, we don't have 1. It's usually 2 to 10. But most of the time I see 3 and 5. 3 and 5. So again, it's still, these things are it's kind of personal decisions that you make. Because what I may feel is right, somebody may not think it's right. So it's just what you feel. But usually for me, I think we are trying to, these days, everybody is trying to develop smart ways or smart AIs that can answer or respond in milliseconds. I don't know if you followed the recent deep research model from Elon Musk's Grok 3. If you see, I do Elon Musk likes to kind of hype his stuff very well. But again, I've tried my hand on it to see how it performs, and I noticed the speed was quite better than DeepSeek and also ChatGPT. So again, the speed is quite something that a lot of people are looking at these days. You wouldn't want to keep something that takes you forever. So that's why we're beginning to really look at those things, because we need to look at speed. We also need to look at computational resources. So again, if you're fine, that you feel you have the time, the resources, you want to train up to 10, it's fine. So again, it's just choices. So any other question? Okay. Any other question? Okay, so I think we can go to the practical section of the class now. So the first thing you do, you come to